All right, this is section 1.4, the chain rule, the rule of chains. So let's go ahead and derive this rule of chains here. So let's recall, okay, I'm going to assume you know this, okay, you should know this. We covered this in our first ever video, so I'm going to assume not only that you have this, you remember this and why this is what it is, but also how to apply it, okay? So limit delta x approaches 0 of f of x plus delta x minus f of x all over delta x, okay? This gives us the derivative. This is the limit definition of the derivative, okay? So now, okay, we're going to let y equal to, f of g of x, okay? And so now I want to find dy dx, okay? So in order to find dy dx, I just do d dx on both sides. Again, I'm just using Leibniz's notation here, again, to show that the derivative is an operation, okay? This is completely valid. I'm doing the derivative of on both sides. So with this, dy dx is equal to d dx derivative with respect to x of f of g of x. So again, we're just trying to find the derivative of f of g of x. Now hopefully you notice here that f of g of x is a composition of functions, right? So we're putting g of x, which is another function, as the input of f of x, which is also another function. Okay, so now if we do this, don't overthink it. It's literally just going to be the limit as delta x approaches 0 of f of g of x plus delta x minus f of g of x all over delta x. And so now I'm going to do a really weird manipulation thing here. Even though it's completely valid in the world of algebra, the world of mathematics, how you actually get this is a little weird, but it makes sense actually once you derive it, like why we're doing this. But for now, it's going to make no sense. But what I am about to do is completely valid, and that's just multiplying the numerator and the denominator of this thing we're trying to take the limit of by g of x plus delta x minus g of x. So I'm literally just multiplying the numerator and denominator by g of x plus delta x minus g of x, okay? Completely valid because, I'm saying multiplying the numerator and denominator by the same thing, right? Valid property of algebra, math, fractions, right? And hopefully this makes sense because if you can literally just cancel these out and this becomes this times 1, which is just this. So completely valid. Okay, so now we're just going to do some rearranging here. So we're going to get the limit as delta x approaches 0. And what I mean by this rearranging here is I'm going to, again, completely valid in the world of math. Okay, this may not make sense, like why we're doing it. Like, again, it's possible. We can do all this stuff. And hopefully it makes sense why we can do it because it's just algebra and rearranging. But so that should make sense. But why we're doing it will make sense later. Okay, but for now, I am actually going to put this denominator with this numerator right here, and then this denominator with this numerator. Okay, and what I mean by that is we'll get the limit as delta x approaches 0 of f of g of x plus delta x minus f of g of x all over g of x plus delta x minus g of x, and that times g of x plus delta x minus g of x all over delta x. Now, hopefully you remember from your properties of limits that you can rewrite this as two separate limits, right? Limit as delta x approaches 0 of f of g of x plus delta x minus f of g of x all over g of x plus delta x minus g of x times the limit as delta x approaches 0 of g of x plus delta x minus g of x all over delta x. Now, there's something you should hopefully notice with this guy right here, okay? Now it's kind of making sense why we did this random multiplication of numerator and denominator, okay? So this guy right here, look at this guy and look at this guy. this gives us f prime of x, right? F prime of x, again, I'm just using Lagrange's notation here. Again, we can mix and match our notations, that's fine, like dy dx, right? Same as y prime, or in this case, right? This will be f prime of x is this. So if f prime of x is this, and we're just having it in terms of g, this is going to be g prime of x. Okay, so now we're literally just going to have this limit right here. Okay, this limit as delta x. I'm going to actually move over here a bit. So don't mind if I do. Okay, it's going to be equal to the limit as delta x approaches 0 of f of g of x plus delta x minus f of g of x all over g of x plus delta x minus g of x. And remember, this guy right here, we're going back to this guy. This is f prime of x. Again, hopefully this makes sense from the last like 3 videos, like why this is what it is. This will be times, instead of f prime of x, this is in terms of g, right? G of x plus delta x minus g of x over delta x. This is in terms of g. This is going to be times g prime of x. Okay, because this limit right here is the same as g prime of x. So now we have to deal with this weird limit right here. Okay, we have to deal with this guy. How are we going to deal with this guy? So now we're just going to, deduce some things based off of this limit. So let's make it simple here. I'm going to say let, I don't know, something like this. Let n equal to g of x plus delta x minus g of x. Okay, so hopefully you realize here that as delta x approaches 0, so what happens as delta x approaches 0, right? Pretend for a minute that we plug in 0 in here for delta x. We do kind of like a direct substitution here. We get g of x minus g of x, which is going to be 0. Okay, so n will be 0 then if we directly plug in delta x. But remember, or plug in 0 in for delta x. But remember, this is delta x is approaching 0. So as delta x approaches 0, that means n must also be approaching 0. Hopefully this makes sense. Because with this equation here, as delta x approaches 0, delta x is getting it's getting very, very small, towards the point where it gets 0 to 0, and then we have g of x minus g of x. But then we have g of x minus g of x. We see here that n is also going to 0. Okay? So hopefully that makes sense, right? Just think about it, right? G of x, delta x, again, it's not equaling 0, it's approaching 0. So as delta x is approaching 0, then this n value is also approaching 0, because then eventually we'll get to like that g, not like, you get what I mean, but like that g of x minus g of x is 0, so n will also be approaching 0. Okay, so now all we got to do here is just rewrite stuff now. So we have limit as delta x approaches 0. So now we have or not delta x, n approaches 0, right? N approaches 0. And now we have f of g of x plus n minus f of g of x all over n. Okay, how did I get this? Well, g of x plus delta x is, look at this guy here. G of x plus delta x is equal to n, so let's just do some rearranging here. If n equals to g of x plus delta x minus g of x, then g of x plus delta x is the same as g of x plus n. I'm adding a g of x on both sides. Hopefully that makes sense. I'm just adding a g of x on both sides. So I'm moving this g of x over to this side of the equation. So we get g of x plus delta x equals to g of x plus n. So that's how I get, instead of g of x plus delta x, I'm getting out of this world of delta x, I'm getting into this world of n. So I'm just putting g of x plus n, okay, instead of g of x plus delta x. Okay, and then we can keep this f of g of x here, and we'll have it over n. So now, let's see what we're dealing with here. Okay, let's you know the saying, like, never forget your roots. Let's go back to our roots here. Limit as delta x approaches 0 of f of x plus delta x minus f of x over delta x. Doesn't this kind of fit that form? Like, I'm going to draw a thought bubble here. Okay, this thought bubble, I don't want it to count towards my work, okay, because it's going to violate, like, if I'm going to just say a delta x here, like a delta x2 or something like that. Okay, so let's say that our n is some other delta x, okay, right? And then let's say that x was our g of x, right? So if we do that, then we'll have the limit as, and I'm going to plug these into, I'm going to substitute n in for delta x here. I'm going to sub in x in for g of x here. So we get the limit as delta x approaches 0 of f of x plus delta x minus f of x over delta x. And wait, right? I didn't forget our roots here. Look, I'm back to the origin. I'm back to where we started. This is the first video. This is in the form of that. But in this case, our delta x is n, and our x is g of x. Okay, like, again, I'm drawing this in a thought bubble here, not to get you confused with this x and these x's and that x's. Like, this n is not equal to this delta x. No, this n is equal to g of x plus delta x minus g of x. But I'm just letting you know that this fits the form of our limit definition of the derivative, where in this case n is in the place of this delta x right here, and x and g of x is in the place of this x right here. Okay, so just keep that, don't get mixed up with these delta x, this delta x and this n. I'm just saying that it fits this form. So if it fits this form, we know that this is, like, this would be f prime of x equals to this guy, right? F prime of x is this guy. Okay. So in this case, f prime, I forgot to add the g prime of x here. Our f prime, we have f prime of x, but what is our x? Our x is g of x. So f prime of g of x times g prime of x. Okay, it's a lot to process. Let's go through this again. This right here, maybe a bit confusing. This right here, this limit right here, okay, this g prime of x is fine. We dealt with the limit that yields us that g prime of x already. This limit right here fits the form of the limit definition of the derivative, where in the limit definition of the derivative, this g of x takes the place of this x, and this n takes the place of this delta x. So I'm just writing my thoughts, like, this is what I said, this is what I'm saying right now. That n, this n, or this delta x is this n, and this g of x is this x. So that's what I've written my thoughts down here. That's why it's in the thought bubble. And so we know that then if it's in this form, I deduced, right? If x is this, if x is g of x, and then delta x is n, we substitute that into this guy, we get our limit definition. So in this case, remember, our limit definition, again, is f prime of x. So we're going to have the f prime still, but then our x is g of x, right? We put g of x for this x. So hopefully that makes sense. Again, ask as many questions as to clarify, like any clarification questions in the comments below. I'd be more than happy to answer them. But hopefully this kind of makes sense, right? So this fits the form of the limit definition of the derivative. So I'm able to deduce that this would yield us f prime of g of x. This limit right here would equal to f prime of g of x. And then, of course, we can't forget this g prime of x, which we already got by evaluating this limit right here. Okay, so we can say therefore, again, this is a very fancy symbol in math for therefore dy dx, or we can just say like d dx, right, like before, of f of g of x, the derivative of f of g of x is f prime of g of x times g prime of x. So what is the significance behind this? So I kind of hinted earlier in the video that this is a composition of functions. This is a generalization for a composition of functions, is f of g of x. For example, going back to algebra 2 or whatever, let's say f of x is x squared and g of x is like x plus 5. F of g of x is going to be the same as f of, and then in this case, g of x is x plus 5, and then f of x plus 5 is x plus 5 squared. So this is a composition of functions. So we can essentially set our f of x to something, our g of x to something, and we can use this general form to actually evaluate the derivative of this. Okay, so it's going to be a shortcut, okay, essentially. Okay, but in order to properly utilize this shortcut, we are going to need some of our other shortcut rules, okay, to make this more effective. Like, for example, you can, right? If we wanted to take the derivative with respect to x of, I don't know, x plus 5 cubed, for example, something like very similar to what I just said, okay? So using our chain rule, right? Chain rule meaning we're chaining it, like we're doing the derivative of the outer function and then doing the derivative of that and then plugging in the inner function, then times the derivative of the inner function. Again, it doesn't really, it may not make a lot of sense now because we haven't done practice problems and this is very general form. But if you want to do this derivative, again, firstly, you can do the limit definition. Or you can say to yourself, well, I know that in this case we can say f of x is x cubed and our g of x is x plus 5, right? And this makes sense because f of g of x, if we do f of g of x here, composition of functions, we get x plus 5 cubed, which is this guy. Okay, so then, of course, using our rule here, well, f prime, again, if you do f prime using our limit definition, okay, again, I'm going to use a shortcut rule here, but we haven't learned shortcut rules, so just do the limit definition on this guy, and you'll get, well, f prime of x is 3x squared. And then remember, we have to do f prime of x, f prime of g of x. So f prime of g of x, what is g of x? X plus 5. So f prime of x plus 5 is 3 times x plus 5 squared. And then now we need to do that times g prime of x. So what is g prime of x here? Well, okay, you can use our limit definition here, or you can just understand here that the slope of this is 1. Okay, so the slope of all at every point of g of x equals x plus 5 is 1. So, and remember, derivative is the slope, tangent line at a particular point, and all the slopes of all the tangent lines. The slope of the slope at every point on x plus 5 is 1, right? Because it's just a straight line. Slope here is always 5. Slope here is always 5. And from negative infinity to infinity, slope is always going to be 5. Okay, so hopefully by that deduction, you can say that g prime of x here is going to be 1. So remember, if we want to do derivative of f of g of x, that's just going to be f prime of g of x times g prime of x, which is 1. So that's just going to be 3 times x plus 5 squared. So that's our answer. We literally found the derivative of this. Again, we didn't do limit definition with this because then that would be really annoying if we did limit definition with this. Okay, limit as delta x over to 0 of x plus delta x plus 5 cubed minus x plus 5 cubed over delta x. This would take a while to do, and it's also kind of confusing how to act, like foiling this out. It's a little annoying. You know, you have to put parentheses here and stuff like that. It's annoying. So we just saved a lot of time by using this rule. And again, we will save even more time once we learn our shortcut rules and stop using the limit definition. But for now, again, it's important that we know the limit definition. Okay. And now you may be wondering why we're skipping all the way to the chain rule before learning the shortcut rules, as typically many calculus classes they do the shortcut rules first. Well, this course is going to be a little different because we're actually using the chain rule to prove our shortcut rules. Okay, so our next video is going to actually completely steer away. Like we will go completely off the typical path, and we're actually going to skip all the way to the derivative of e to the x and then to the natural log of x. Teachers really do not do that until they've fully finished these regular derivatives of like polynomials and stuff. But the reason why is because, well, you will see. Okay? So again, this is very different from a typical Calc 1 course because we're actually doing it in a very different way, but I think it's actually a better way than pretty much every single other Calc 1 course. Now, I'm not trying to be arrogant or cocky, but you'll see why. It makes a lot more sense in this way. Okay, so yeah, let's move on to the next video. Yeah, hopefully you found this makes sense. Again, ask questions in the comments. Cool.